Hey there, math fans. Since I just did a video on string and peg art, I thought I would make the part 2 because I already had it ready. So for part 2 of my little analysis, what I'm going to do is take 2 lines here. So what we did before was we talked about what if we have a horizontal and vertical line and we make these dots equally spaced. 1/5, 2/5, 3/5. And then as in grade school, somebody once showed me that if you connect this last dot to this first dot and so on, all the way through, you get this kind of cool shape. And then in a recent video I talked about there's another way that this is sometimes done, which is you ignore the last dot and you connect these two. And that gives a little nicer analysis. So anyways, that's the one from the more recent analysis, and we found this function. There's probably a lot of ways you could go from here. So my next thought was, this doesn't look like a typical parabola in terms of the x and y coordinate system. So I wanted to see, could I get a vertical or horizontal parabola? So I rotated things a little bit. And so I thought a reasonable next step would be, what if you had a line of slope m and a line of slope negative m? And there's other things we could do. What if the slopes aren't the same? What if they don't go through the origin? There's plenty of questions, but I'm going to kind of do it in small pieces and kind of build this up a little bit. And certainly there's other people that have analyzed these. I'm just giving you thoughts of how maybe a mathematician would think and generalize. And since I'm not a mathematician, I don't know why you're listening to me. I'm a math teacher. Anyways, been teaching math for a long time, and hopefully you'll get something out of this. So I'm going to do both analyses where you connect with that. It doesn't take much more work, and I'll do them side by side. I have it on this page in just a moment. And then I'll share this with you. So first, if I connect, there's not using the last point. And here is using the last point. And the natural question is, what if you equally space them going 1 unit out? I didn't do that. So I did the same analysis in terms of x, meaning I went all the way out to x equals 1. That's x equals 1 and x equals negative 1. And I treated this kind of like the y-axis was in our last one, so I connected this point to that point in one of the setups. That's this setup, what I'm calling g of x. And then here's the envelope setup from the last video. So I'll look at both. Once again, they both approach the same thing, but this one has this nice behavior. And this one's cleaner. The analysis is much cleaner because it's symmetric. So you get this really nice curve. I can give a nice formula for it. Ooh. And I have these thoughts. I'm sure people have done this with, you could make a pegboard, put your little staples in and use rubber bands or string or whatever you want. And you could say, well, I would like a parabola of a certain shape. And that's kind of what I'll do in the next video, is match. You give me the parabola, I'll tell you how to make it with your art project. So the question would be, what lines do you use? Should we shift it up or down? But for this video, let's just talk about 2 lines to the origin. One has a positive slope, the other one has the opposite slope. And we'll look at these parabolas. So you can see we've already solved it, and the answer's sitting there. If you do the other version that I was gonna do before one of our viewers gave us the nicer interpretation, you get that it still approaches, but it is slow, as we saw in our previous one. It does approach, there's a little bit of an error. It gives you a little bit of an over approximation in some sense. Whereas if you do the other one, this hits it right on. The points themselves are below, some of these intersection points are below the graph, but looks way better. So now I understand why more people do it that way. But I'm going to keep, maybe there'll be something we'll gain from this other one. It's kind of cool too. And we don't have to leave that last peg. Okay, so the answer I'm getting is m over 2, so whatever the slope is, divided by 2, x squared plus m over 2. So you can start to see if you wanted your parabola to go through the origin, we're probably going to need to shift down our lines by m over 2. And we'll do that in the next video, but I'll do a more general analysis of you give me a parabola, I'll make the art project that fits. Okay, so let's look at our analysis here. And I mimicked, I'm trying to just do the exact same analysis as the previous presentations. We're trying to generalize. So here's the envelope approach with just a few of these. And my approach was to find the intersection points and then to see where they go. And then use the fact that the slope near that intersection point will be the same as the slope of the lines, and that'll get closer and closer. So I asked the following question. What's the intersection of the 2 points in question? The 2 points in question are, if I give you one of these, oops, I did not mean to do that. If I give you this point, I over n, then the y value should be m times I over n. And then the corresponding point over here, if you're doing the envelope approach, is this. So I'm doing, in the last video it was 1 minus I over n, and it was on the y-axis. Now we're going to take that and flip it to the other side. That's what we're doing. And then we're plugging that into here, and because of this negative and that negative, it's positive here. From there on out, it's a bunch of arithmetic algebra. To find the slope, you're going to do this y minus that y over this x minus that x. I did all of that messy work by hand, then I checked it with Wolfram Alpha, and I got this. It goes through this point. I didn't even find the y-intercept. Well, yeah, I didn't find the y-intercept because I didn't need it. I just wrote that. Then I plugged in I plus 1 to all these places and found the intersection of this line with the corresponding line with an I plus 1. Had to check that with a solver, and I got this point. So there's a nice formula for where these corresponding intersections are of consecutive lines. And I did the same trick from last time, which is I'm going to assume that the slope at a given x is going to be the same as the slope of this line as n goes to infinity, that it's going to approach in that way. And that's different than the other approaches that assume this tangential piece, but it still should lead to the same thing. I did the same trick where I solved for I. This time it was easier to do. I replaced this I with that, and then I got to do a limit question. And that limit is much cleaner. You don't need any limit tricks to do it. It just came out to be mx. So the derivative needs to be mx, so we can integrate, and then it's going to be x squared over 2 with the c. Figuring out what c should be wasn't, I was trying to do the same analysis as before, but before we get to that, I went over to the other one, and I said, well, what if we do it the same way where we do connect this first point to 1? Then there's going to be this little shift. And you can think about it, you can try it with some numbers. It's the same shift as the last one. It changes the slope. It actually made the intersection point a little nicer because it didn't have this 1 plus on top. I solved for I. I said the slope at a given x will be approaching this. And then I replaced the I. Took the limit. I got mx. That's nice. We got the same thing. In this case, it was easier to see what c was going to be because I knew this last intersection was going to get closer and closer on both sides. And so our curve was going to get closer and closer to 1 comma m. Because when you plug in a 1, you get an m. And so I was able to use that as an initial condition. So this is 1. This needs to be m. And if m equals m over 2 plus c, c should be m over 2. Thus our answer, m over 2x squared plus m over 2. So if you wanted the particular parabola, the standard parabola where the coefficient of x squared is 1, you would need to use a slope of 2. So I thought that was kind of nice. So anyways, let's go back and look at that. So if you want the parabola x squared, let's save this. Apologies there, I clicked the wrong thing. Let's save this, and let's make the slope exactly 2. And let's zoom out so we can see it. And that parabola is x squared plus 1. It shifted up 1. If we didn't want it to be like that, we would need to shift our lines down 1. Now that's going to change some of my formula, so I got to be a little careful about that. So maybe I shouldn't do that here. We'll save that for the next video where we shift everything down 1. It can be accomplished. And then we could also shift it over and to the right, and we'll talk about that. I have not done the analysis yet where the two slopes are different, but certainly we could draw it. The question of finding the equation might be a little more exciting because it's going to be a turned parabola a little bit. But anyways, hope you found that interesting. Let's draw both of them. So that will also approach, but it's going to, if you're not getting this nice picture. So if you're doing an art project, it's better to do the envelope approach to get this parabola. And it's kind of pretty. I like this visual of these things, and you put in a whole bunch of these. Just a fun little game. Mostly if you have a niece or nephew, someone in your family, you're trying to occupy some time, just draw a couple lines, put some equally spaced points, and start connecting them. And you can say, hey, I saw once on a video that gives you some sort of parabola. And then you'll have remembered me. All right, thanks for listening.